The next step is to establish a relationship between the statistical distance and something that's a bit more, at least from a technical perspective, a bit more useful. In particular, we're going to slowly develop a result known as the leftover hash lemma, which tells us that if you have a particular kind of hash function, in particular, one with a weak kind of collision resistance that we've already covered, epsilon almost universal. If you have an epsilon almost universal hash function and you use it as an extractor, it turns out that it does a good job of turning reasonably high min entropy strings into strings of bits that are all individually, essentially random bits, uniform random bits. And we're going to develop this result in stages. And the first part of this result is establishing a relationship between the statistical distance between x, the random variable we care about, and the uniform distribution. We're going to relate this to something called the collision probability of x. So, as this name suggests, the collision probability is the probability that if you were to sample twice from the distribution that underlies the random variable x, and you saw values x and x prime, the collision probability is the probability that x and x prime are in fact the same. So it's a collision, it's a sampling collision essentially. Looked at another way, the collision probability CP of a random variable x is the probability that a random variable x equals another random variable x prime, where x and x prime both have the same underlying distribution d of x. So if you expand that, well, of course, x can be equal to x prime if they're both equal to the first x in the set or the second x in the set or so on. So this thing is equal to the sum over all possible values that either x or x prime can take. And because these two random variables are independent, this of course would be x equal to little x and x prime equal to little x. But since they're independent, we can just write this as the product of their probabilities. And because x and x prime are identically distributed, namely they have this underlying distribution here, because of that, this is just the square of one of their probabilities. So this is the definition of a collision probability of a random variable x, and this is how you can compute it. So what we're going to do is establish a relationship which is pretty unintuitive, to be honest, between the statistical distance between x and uniform and the collision probability. And in particular, here it is, that the statistical distance between x and uniform is upper bounded by 1/2 the square root of the size of the set of values that x can take times the collision probability of x minus 1. I will agree with you that that is not an intuitive result at all, but it is interesting because if you notice, the uniform random variable is gone. The entire bound here is strictly a function of the random variable we care about, x, so the sample, the string of bits from the non-uniform but high min entropy, we hope, source, and the size of the possible values that it can take. That's kind of handy. We've sort of gotten rid of the uniformity and allows us to focus directly on the random variable that we care about. So this results, it's a little mathy, but it's really not that hard. It has one kind of advanced step in it, so we're just going to go through it quickly. So here's the proof of this. The first thing we do is, this 1/2 is kind of a distraction, so we just move it to the other side. So twice the statistical distance between x, the non-uniform random variable, and a uniform random variable over the same set is just this, as we established above. And then we apply what's called the Cauchy-Schwarz lemma, or the Cauchy-Schwarz inequality. And if you don't know this, you should. It's one of the most useful inequalities in all of mathematics, at least in my opinion. It just pops up everywhere. And Cauchy-Schwarz, if you don't remember it, relates the sum of a product to the product of the squares of the sum. So in particular, if you have the product of a sequence of values ai times bi, and you sum that up, so it's like a1 b1 plus a2 b2 and so on. This is upper bounded by each of the individual ai's squared. You take the sum of those, so a1 squared, a2 squared, a3 squared, and so on. You add those up, you take the square root, and you multiply that by the same thing with the bi, so b1 squared plus b2 squared, and so on, square root. So we apply Cauchy-Schwarz moving from here to here. So these are the ai's. And then implicitly here are a bunch of 1s. So each one of these terms you can think of as being multiplied by 1. So those are the bi's. So when we apply Cauchy-Schwarz, here's our square root, which is these half powers here. So we've got the sum over all possible values of x of our ai's squared times the sum over all possible values of x of our bi's squared. Well, the bi's are just 1, so 1 squared is 1. And so this summation here just is the size of the set cal x. Okay, so that's really the only real mathy step that's here, applying Cauchy-Schwarz. Moving from here to here, all we've done is we've gone from absolute value squared to just the square of the difference. And you can see that that makes sense if you just look at the picture here. The absolute value, if you take the absolute value, even the negative values, then we basically reflect this up top. And so when we square it, we're just getting a positive value. But of course, if we square it, we get a positive value anyway, even if the difference is negative. So it's fine to remove these absolute values and just move to here. And then we simply apply the square. This is basic middle school algebra now. So we're going to get this first term. Now, of course, we have the summation on the outside, but it's going to be this first term squared, summation over x. So that's here. Minus twice this times this. So it's twice 1 over x times the probability, so times this. Again, the sum over all x. But because the 2 and the size of the set are constants, we can just pull them out of the summation, so we're left with this. Plus this term squared, again, summed over all values of x. So that's here. Well, you notice that this is handy because this sum here is just 1, since after all, the random variable has to take on some value. So this just sums to 1. This term here is the sum over all x times this constant. But that's just going to give us one of these, right? It's going to give us the size of cal x times 1 over cal x squared. So that just leaves us with a term of 1 over cal x, because one of the square gets canceled by the summation, basically. And then we've still got our size of cal x on the outside. This term, of course, this sum over the probability squared is just the collision probability. So we have the square root of the collision probability minus 2 over size of cal x, because this is 1, plus 1 over size of cal x. Well, that just gives us minus 1 over size of cal x. So when we distribute this through, we get the size of cal x times the collision probability minus 1, take the square root, and that gives us our bound here. Okay, so now we've related the statistical distance between x and a uniform random variable to the collision probability, and we've gotten rid of the uniformity altogether. And now we get to the real crux. This was just a technical tool that we need. Now we get to the crux of the leftover hash lemma. It says this. Let's say you have a hash function, and it takes in keys, but remember when we talk about hash functions, keys are really just indices into a function family. They're not secret. We've got a function family keyed by this index. It takes elements from the ground set of the random variable, so cal x, and it outputs a string of m prime bits, which is the parameter that was in that definition we just looked at a moment ago. So we have a hash function, and in particular, if it is epsilon almost universal, and you'll recall that this is a very weak kind of collision resistance where you have to fix 2 elements of this set first, because it's for all for all pairs of elements from the set that are different. If I then pick one of these indices uniformly at random, the probability that you get a collision is epsilon. Recall that's the definition of epsilon almost universal. So here's what we're going to do. We're going to define a new random variable z to be a pair. It's going to be the index into the hash function and the result of running the hash function named by this index on the random variable. In other words, you take a sample from the underlying distribution, you hash it using this particular index, and then the pair goes together. That's our random variable z. In particular, this is sampled uniformly. This index is picked uniformly, and this is picked according to that underlying distribution dx. And importantly, we're going to assume that the distribution that underlies the random variable is independent of the choice of the hash function. So the entropy source itself can't depend on the function that we're going to use to hash with. Okay, well, when you have that set up, an epsilon almost universal hash, and then an index into the hash function that's uniform, and then a sample from your entropy source, then we have that the collision probability of this pair is upper bounded by this term. Well, you can see, I think, where we're going with this, because we have a relationship between the statistical distance and the collision probability of a random variable. And here we've got now a bound on the collision probability of a random variable. So we're going to put these together. And in particular, if you notice what this is saying, this random variable is about the choice of the hash function from the family and the choice of the sample from the entropy source. So that's what this z is. But this collision probability is upper bounded by simply the size of the set of keys for the hash function and the collision probability of the underlying random variable that we're sampling from, plus the epsilon of the almost universal hash. So what particular key we've used no longer matters. That's all caught here just in this term here. And everything's going to be simply about the underlying entropy source. So the proof of this is straightforward. There's no fancy math here. It's just conditioning. In particular, the collision probability of this random variable that we defined here is just the probability that some random variable z is equal to z prime, where they are IID. Well, of course, because each of these is actually a pair, if these two are equal, it means that the key k in this pair and the key k prime in this pair are the same, and the hash using that key of a sample from the entropy source is the same as the hash under this key of another identically distributed sample from the source. That's just rewriting, just expanding the pairs out. Well, now we're going to use basic conditional probability. We're going to condition this AND event. We're going to write this AND event as the probability of this kind of collision, given that the keys are equal, times the probability that the keys are equal. We've just taken this AND and written it as a conditional probability product. And we do that because this term's easy. For any value that we choose for the first key, k, the probability that when we sample the key k prime, which is identically distributed, that it hits this key is just 1 over the size of the key set. So that's easy. And we have this remaining term, which is the probability of getting this collision given that the keys are equal. Well, we're going to further condition that. And in particular, we're going to condition this on whether or not the inputs to the hash functions are equal. So here's our collision events. This is the thing we were conditioning on. Now we're going to add to that the condition that x is not equal to x prime, meaning we have two different inputs to the hash function, and the keys are the same. So this is now the sort of standard kind of collision that you think about. A hash function indexed by the same value, so it's one hash function with two different inputs, x and x prime. Well, we already know that same key, the keys picked uniformly at random, the inputs are different, and we have a collision. Well, that's just the epsilon and the epsilon almost universal, times the probability that x is not equal to x prime. Well, we can just upper bound that by 1 because we can always upper bound a probability by 1, so that's just going to go away. What remains then is getting a collision when the keys are equal, so it's the same hash function, but now the two inputs are equal. Well, of course, that's probability 1. Same inputs, same key, same value, so that's 1. And this is simply the collision probability of x. So just by some simple conditioning, we get this bound on the collision probability of the pair is just a function of the size of the function family of hash functions times the collision probability of the original underlying distribution plus epsilon. Okay, so now we can put this all together. We take this result and put them together, and we get that twice the statistical distance between this random variable, which we called z a moment ago, and the equivalent uniform random variable. So this random variable is over the set cal k cross bit strings of length m prime. Not necessarily as a joint random variable, this is not uniform necessarily, right? This piece is, but this piece is not necessarily so. We're going to compare that to the uniform version over that same set, that same Cartesian product set. This is uniform over cal k, and this is uniform over this. And we can apply the first claim, which shows us that the statistical distance between this random variable z and the uniform version of it is upper bounded by, if you plug things in, this term here. This is just the collision probability of z. This is this term here, the size of the underlying set. Well, the size of the underlying set here is the size of cal k times the size of this, and of course that's just 2 to the m prime. So just by plugging into the first claim, we get this. And, well, what's the collision probability here? The collision probability, we're just going to roll in this bound to it that we just used a moment ago. So we can replace the collision probability of z, this thing, by 1 over the size of cal k from the hash function, plus epsilon of the hash function, plus the collision probability of just the underlying x. Simplifying this then, we get the final result. And that is that the statistical distance between this and this, the actual random variable and the uniform version, is upper bounded by 2 to the m prime times epsilon from the hash function plus the collision probability of the original entropy source. Okay, let's just pause for a second and see what this is telling us. This is saying, if you're an adversary, even a computationally unbounded one, and I use a little bit of randomness, of actual like seed entropy, if you will, to pick an element of the epsilon almost universal hash function. So that's my little bit of seed for the extractor. The hash function is the extractor. So this is my seed randomness. This now here is the extractor using the seed randomness. We were calling this R a moment ago. This is our seed randomness. This is our extractor running on the input. If I were to show you and say, okay, I've sampled something from my entropy source, that's the x. I've hashed it using this epsilon almost universal hash function, and here's even the hash function. I'm telling you which one it is. If I show you that, and I ask you whether or not I've shown you that pair, or I'm showing you the index for the hash function. So I'm telling you what hash function is, and yet instead of the actual hash output, I show you a uniform random string. No? This is saying that no test, even a computationally unbounded test, can distinguish between seeing the seed randomness and the hash output and seeing the seed randomness and a uniform bit string of the same length. That the best that any such test, even a computationally unbounded one, can do in distinguishing, in particular, the extractor output from a uniform random string is at most this. And that's powerful because what that tells us then is that we have a way, a way to create an extractor quite simply using an epsilon almost universal hash, which we know how to build. That's pretty handy. Now I wanted you to observe something. We still have this collision probability of x in here. And now we're going to roll back to our min entropy because that's our measure, right? We're told we have this entropy source, and that for a sufficiently long string, so you keep sampling a bit from this source over and over and over again, that for a sufficiently long string, you're going to get some guaranteed amount of min entropy. So I want to relate now the collision probability of that long string x. Keep in mind, back to this picture, this is our long string x, this is our seed entropy. In this particular construction, this is the index into the hash family. This is running the hash with that index on this long string, and this is the output. And going back, okay, so this is saying the collision probability of sampling that long string. This is just the definition of it. Well, look at this. This is probability of x equals x times the probability of x equals x. Well, one of those, I'll just go ahead and upper bound by the maximum value, the maximum probability. Of course, the maximum probability is a constant, so I can pull it out of the sum. And this sum, as we saw before, is just equal to 1, right? So in other words, the collision probability is upper bounded by the max probability, the most likely value, and that by definition is 2 to the minus min entropy. So that means we can take this now and stick it back in here, and we have a full relationship for our epsilon almost universal hash extractor. Here it is. Hence, if you have, so this is now rolling back to that definition we looked at a little while ago from the HKDF paper. If you have a hash that takes in, this is the index set, so we have t bits of seed randomness. They're going to pick which hash we're going to use. And then we take an n-bit string x. What I was saying earlier, think of n as being like a large number. And we're going to output an m prime bit string. If this thing is epsilon almost universal, x is a random variable over the input set with some guaranteed min entropy m, then we get this result here, that no adversary, even computationally unbounded, can distinguish between the hash output and a uniform string with probability better than this. Epsilon times 2 to the m prime plus this term here, which is, if you look at this, the length of the output of the hash function minus the number of bits of min entropy that we had in the source to start with. In particular, if your hash is universal, not just epsilon universal, but truly universal, and these are also not hard to make, then by definition, epsilon is equal to 1 over the size of the range of the hash, which is 2 to the m prime. So if you stick that in for epsilon, you get that this very simple upper bound for a universal hash, that no test can distinguish between the hash output given an input that has only min entropy, not uniformity, but min entropy of m. You can't distinguish between the hash output on a min entropy m sample and a uniform string of the same length with probability better than this. Well, what is this telling us? We want this probability, we know it has to be less than 1. So what does that tell us about, let me zoom in a little bit here. That's a little better. What does that tell us about these parameters? Well, first of all, you're going to need this exponent to be negative, right? Because we're going to need this statistical distance. It's always going to be upper bounded by 1, because that's a probability. So this is going to be m prime minus m has to be negative, which tells us already that you can't output more bits than you had bits of min entropy to start with, if you want to be close to uniform. And in a way that makes sense, right? If you're trying to turn a non-uniform string that has some kind of entropy in it into a string that has full entropy, if you will, then you can't hope to output more bits than you had bits of entropy to start with, right? So m prime is going to have to be less than m. Yeah, and so, in other words, when you zoom back out here now, if you have an epsilon universal hash with epsilon that's close to being universal, and an output length m prime that's much less than m, so you're going to have to compress, or if you have a fixed output size that you need, you're going to have potentially a long input string, the length of that string depending on how much you need to get the min entropy that you require. This epsilon universal hash gives us a way to extract m prime nearly uniform bits from a non-uniform source. Of course, under this assumption that the source itself is independent of the hash. In other words, the source can't be somehow using this hash function in order to generate its bits. That's kind of a pathological thing anyway. Okay, so let's see what that means. So let's try to break this down with an example. So that means if you want the output of your extractor, your hash, to be delta close to uniform, even when I tell you what hash function is that I used, then we just have to set this bound that we had, this bound here, which is the general form for an arbitrary epsilon, to be upper bounded by a delta. Or if you rearrange things slightly, you get this, right? Just by moving this to the side, squaring things, and taking care of stuff, you get this. And this allows us now to look at a trade-off between how good the hash function is, epsilon, how large the hash output is, m prime, the so-called entropy gap between the min entropy that you get from the source and the uniform that you want, right? If you had 2 to the minus m prime, that would be a truly uniform string. So this is like the entropy gap between the hash output and the min entropy that was going in. This thing has to be upper bounded by this term. So we have now a way to sort of play with these numbers and figure out, if you have a fixed, say you have a fixed hash output, you have a fixed delta, then you can figure out things like, okay, how many bits of input do I need, and so on. Let's look at an example. So let's say that you need 128 bits of extracted key material. So you're trying to make an AES key. Well, that means m prime has got to be 128. and you want this 128 bits of extracted key material to be at least 2 to the minus 80 close to uniform. Meaning, if we think of 2 to the minus 80 as being a number if we think of 2 to the 80 as being a number of computational steps that's well beyond the reach of any reasonable, even highly parallelized algorithm, then having something be 2 to the minus 80 close to uniform is a good target. So that means our delta is 2 to the minus 80. If your hash function is universal, so we're going to use this bound here. If it's universal, meaning that epsilon is 2 to the minus 128 because that's the size of the output of the hash, then by rearranging we get that m, the amount of min entropy you need, and this is strictly by just taking this expression and doing the logs and all that, m has to be at least this. So m has to be at least the number of bits of output that you want, plus this term here, which has to do with the closeness, the goodness of the hash, and the size of the output. So you need at least min entropy number of bits, that's the number of bits you want to output, plus this term here, which is all due to sort of the processing factor. If you plug in the numbers, delta we said is 2 to the minus 80, so when you square that you get 2 to the minus 60, but you multiply that by 4, so 2 to the minus 158, minus epsilon, which is 2 to the minus 128, times 2 to the m prime, which is also 2 to the 128, so that becomes a 1, plus 128, which is the size of the output. You take log of that, and we get 158, so this is going to come down, the negative log gets rid of the minus sign here, so we get 158 plus 128, which says you need the min entropy to be at least 286. So then what that tells you as a designer is I need my entropy source, my entropy harvesting routine to collect up enough bits to be able to guarantee me 286 bits of min entropy in order to be able to extract 128 bits of randomness that is so that every bit in there, that the whole string is effectively uniform. It's 2 to the minus 80 close to uniform. So now what you can do is go look at your entropy source, which, for example, may be a hardware source, or it could be, like we were talking about earlier, interpacket arrival times and keyboard strokes and mouse clicks and whatever. And you can back out from your model there how many bit samples you're going to need to create a string to get 286 bits of min entropy. And once you have that, you know then how long those strings need to be to get what you need. Well, okay, that's a lot of work. It's actually a really lovely result. It's a famous result. It has this funny name, leftover hash lemma. It's appeared in multiple places under different names, but that's the one that seems to stick. And it's really nice because it gives you the ability to say, I have a very simple way, namely, just give me an epsilon universal hash function, which we know how to build, buffer up enough samples from my non-uniform source to get the min entropy that I need, then hash it. And I can then show you the hash function that I used and the output of the hash, and you can't distinguish it from uniform. And now that means I can take the output of the hash and use it as a key, like a true key for my system. In particular, notice if you have a PRF F, it takes in a k-bit key and an L-bit input and outputs an S-bit string. If you have a PRF and you have a way to extract a k-bit string that's close to uniform, so you need like a key for this PRF, that's what we're doing. If you can extract from your non-uniform entropy source a k-bit key for this PRF, then you can just create lots of keys now by calling the PRF on the input of all ones, calling it on the input of all twos, and so on. And this gives us a way now to turn an extracted, truly uniformly random key, or at least close to it, delta close to it, and use that single extracted key to generate lots of keys that are all now computationally indistinguishable from random. So this is a really nice result, because once you've spent the time to harvest your entropy, hash it once to get a key for a PRF, then you can use that PRF to create an arbitrary number of keys that you can use for arbitrary uses. And we've seen examples of using a PRF to turn one key into many keys before. And in particular, if the extractor gives you a key that's delta close to uniform, then what you get is that there's no efficient test. So no efficient test will be able to distinguish between these two produced keys from the PRF. So K1 and K2. No computational test can distinguish between these two produced keys and two uniform strings of the same size, with advantage more than twice the PRF advantage, which is coming from these two PRFs, twice the PRF advantage, where the complexity parameters are quite small. So the running time is O of L, which is the size of the inputs. Only 2 queries are made, 1, 2. The length of those being twice L, because that's the length of the inputs to the hash function. You can't distinguish between these 2 keys and 2 truly uniform strings with probability better than twice this PRF advantage plus delta, where delta is the closeness of the original PRF key to uniform. This is really a nice result, because it gives us now a way to combine our extractor, which is just an epsilon almost universal hash, and a PRF, which we already know how to build, to create effectively an arbitrary number of keys. In fact, here's a typical, what I'll call a randomness pipeline. And this is roughly what, so every Intel chip from like 2008 or 9 on actually had built into it a hardware entropy source, a hardware random number generator that then is run through an entropy extractor and then run through the same kind of extract and PRF construction to create. So there actually are instructions, read rand and read seed, in the Intel instruction set, which allow you to pull randomness at the instruction level from the hardware. And here's what that pipeline looks like roughly. There's some hardware entropy source that's on chip. It's a physical Zener diode based kind of process. And it's guaranteed by just the physics of the device that you get some fractional number of bits of min entropy per bit sample out of this entropy source. So you keep the hardware keeps sampling from this entropy source, and it buffers those up. And as it's buffering, it's running some health tests internally to make sure that it's not getting if it gets a whole bunch of zeros in a row, then that tells it that the entropy source has probably been starved and you need to wait for some thermal processes to change or something like that. But you repeatedly sample from this entropy source into a buffer. And so this whole dotted area here becomes the effective entropy source, because when the buffer releases, it releases a string of enough bits that were sampled from here to give you a guarantee of min entropy, which is actually given to you by the entropy source, because you get a fractional number of bits per sample coming out of the source. So you buffer up until your string is long enough to get a min entropy M that you need. Then that string is passed through the extractor, which is just a hash, or they may be using a slightly different construction, but it doesn't matter. You take this string, you run it through your extractor, and this now gives you a string of essentially uniform, true, statistically close to uniform random bits. So nobody can distinguish this. No even computationally unbounded test can distinguish what's on this wire from a truly uniform random bit string. Well, in normal operation, these uniform bits then get passed to counter mode. Now you remember, if you key counter mode with a uniform random string and then feed it with a message that's all zeros, what do you get out? You get out the output of the underlying block cipher, which Intel has instructions for the AES block cipher. So this is counter mode running over AES, keyed by the output of the extractor on a message of all zeros, and counter mode on a message of all zeros just gives you the raw output of AES, which means you now can get effectively an arbitrary long string of pseudo-random bits, which you can then use for whatever you need it for. This is essentially the Intel hardware random number generator pipeline. It's a very common pipeline. I think this is actually standardized by NIST, this pipeline in particular. There's a couple of feedback loops here. You may use some of these truly uniform random bits as a seed refresh for the extractor. If you run into a situation where you feel like the seed for the extractor needs to be updated, you need some new kind of seed randomness, you can use some of these random bits for that purpose. You also can take these pseudorandom bits, and if you want to update counter mode because you're worried that the PRF security of underlying AES is going to kick in, you can use some of these pseudorandom bits to rekey counter mode, or to be built into the rekeying of counter mode. So what you get is, this is your effective entropy source, is this source plus buffering with the health tests built in. And then this piece here, extract followed by counter mode. Well, and I did want to point out that the read rand instruction reads from these pseudorandom bits. The read seed instruction actually will read straight from here. So if you need truly uniform random bits, you call read seed. If you can live with pseudo-random bits, so computationally indistinguishable from random bits, you call read rand, and that reads from here. Read rand, once you have gone through here, read rand will push out random bits. I forget, I wrote a paper on analyzing the Intel Harbor random number generator. I forget what the rate is, but you can pull pseudo-random bits off of this line here using the read rand instruction faster than you could ever possibly need them. If you pull from here, if you call read seed, it gives you everything off of this line, at which point it blocks counter mode. You can't call either read rand or read seed again. It's blocking until the entropy source has buffered up enough to be able to then extract and get a new seed and so on. So you have these two options, pseudo-random bits, truly random bits. It's a really nice design. But this piece here, this extract followed by counter mode, is an example of what we call the extract then expand KDF paradigm. The idea being here, you have an extractor, which takes in the seed randomness, and some source sample. So that's the seed randomness, and then this is the source sample. And from that, you extract some master key. And then you use the master key as the key for a variable output length. We've talked about variable input length PRFs before. A variable output length PRF is easy to construct given a fixed output PRF just by calling that repeatedly using domain separation. So you take this master key, which is going to be statistically close to uniform. You use it to key the variable output length PRF, along with often some context information. We'll come back to that in a moment, and an output length, how many bits you want, and that produces a string of key material of this length. Why the context info? We have talked before about for good cryptographic hygiene, one should use different keys for different purposes. So if you need a key for encryption and a key for some other cryptographic operation, you should use different keys. The context info enforces that. If you think about running a PRF with the same output length and the same key, as long as you change the context info, this gives you domain separation in this PRF, and so these keys that come out will independent, computationally indistinguishable from just independent uniform strings. So the context info is something that is very, very useful in practice to be able to say, I've got this master key, I'm going to key my PRF, give me a key for encryption of this length. Now I can call this again using the same master key, give me a key for creating a tag of this length, and so on. This is a slightly informal version of the extract, then expand key derivation function paradigm. Okay. Pause.